Okay, so completing the solution here. 3 days during a 2-week period. So the 2-week period is 10 days. So n is 10. Oops, go back to my template. And the probability that Trina claims is 0.4. So 10, 0.4 are my binomial parameters. Okay. I want the probability that it is at most 3 days. So the days range from 0 to 10. At most 3 days. Well, that's 0's okay, 2's okay, 3's okay, at most 3, doesn't allow 3, 4's not okay. So the probabilities I want are those. So I need to do binomial CD with this value of C and of n and p. So I need the probabilities of values up to 3, so that's my x, and my n was 10, and my p was 0.4. So my answer is 0.3823 to 4 decimal places. Okay, so there we go. Now for the next part of the question, n has changed, p probably hasn't. We've now got an 8-week period, so 2 weeks was 10 days. So for 8 weeks, n is now 40. Okay, p is still 0.4, we think. We're going up to 40 as our maximum number of possible days. But I want more than 10, was it? More than 10, but fewer than 20. So it's not allowed to be 10. It is allowed to be 11. Can't be any of these. Fewer than 20, so it can be 19, but fewer than 20, it can't be 20. So I'm going to get rid of all of those. So I need a box that includes the 19, but I need to exclude these. So what I need to be doing is doing the probability of x being up to and including 19, and I need to be taking away the probability of x being less than or equal to 10, and write that down because there are method marks even if something goes wrong with the calculation, but it shouldn't, because we've now got, make sure we change our n value, so now we've got an n value of 40 days, okay, and we'll have the top limit, which we're going to do first. I'm going to have to go back in. So the top limit I wanted first was up to 19. So my first probability is going to be 0.872. 0.8702 minus, okay, on my second one I wanted values up to and including 10. So I'll put 10 in and I get 0.0352 minus 0.0352, take those away, and I get 0.835 to 3 significant figures. Not totally sure I trust that last one, but 3 significant figures is good enough. Okay, then for part B of the question, we've got yet another change in n, because now we're just dealing over 5 days, but p is still going to be 0.4. So n is 5 days, p is 0.4. The formula for the mean from your formula book is np. So I need to do 5 times 0.4, which is exactly 2. And the variance, okay, which is np1 minus p, is going to be 5 times 0.4 times 1 minus 0.4 is 0.6, which gives an answer of 1.2. But that's the variance. For the standard deviation, I need to do the square root of that variance. So the square root of 1.2, my calculator tells me, is 1.095. 1.095. So I've got my mean 2 and my standard deviation 1.095. Now for the next part of the question, I've got Susie's results, and I need the mean and the standard deviation from those results. So here's my calculator. Okay, I've entered Susie's data. Notice all the frequencies are 1 because it's just a list of raw data. So if I do the 1var calculations from those, it's showing me here that the mean at the top is exactly 2 and Sx is 1.15. So here are my answers, 2 and 1.15. Now we have to comment on the validity of Trina's claims. So if Trina was right, we'd have a distribution with mean of 2 and a standard deviation of 1.095. Actually, I got a mean of exactly 2, and I've got a standard deviation of 1.15. So my own personal reaction would be, this isn't far off. So I would say both the mean and the standard deviation are approximately the same, so Trina's claims might be valid. But you will also get the marks if you say the mean is the same, but the standard deviation is different, because there's no way that you know of knowing what kind of difference in the standard deviation is acceptable. So this is one that you could have had either way. So this is how I would word my solution. Okay, question 6. We've got quite a few words to read, and one of the challenging things about this question is spotting the topic. So, Trina is catching trains. We've got her claim for the probability that the train arrives on time. She claims it's this 0.4. Okay, for the probability, and she also claims independence. Okay, so that's interesting. And then we've got to assume her claims to be true. We've got to get the probability that it arrives on at most 2 days during a 2-week period, and it's kind enough to tell you that's 10 days. So big deep breath. What's going on here? We've had a probability question before on this paper. We've got talk about independent, so we've got some independent events going on, and we've got a fixed number of days. So you have to recognize that we are counting the number of on-time trains in a fixed number of independent days. So that means that's the giveaway to this topic. So this is the topic, binomials, where you are probably going to have to recognize the situation. It might well not use the word binomial in the question, but you know there's going to be a binomial question. So one of the things you can do at the start of the paper is just look through and find it. Okay, so we know that we are dealing with x, whatever x is. X must be the number of on-time trains. So the on-time, there should be number of, I should put, number of on-time trains. And x, twiddles, a binomial distribution, and you're going to set up a value of n and a value of p. Okay. So, and all that should be in your solution template, actually. So, on at most 3 days during a 2-week period, it's going to look like this. You're going to set up your binomial distribution. You're going to be really clear about what n and p are. And then the probability of at most 3 we're going to get. Now, this is where you have to list your possible outcomes. So it always starts at 0, okay? We're interested in numbers around 3, so we'll have 2, 3, 4. You can have dot, dot, dot here. You can have dot, dot, dot up to the maximum number, which will be whatever your n is, will be your top here. And you need to find the probability of at most 3. So you can go through putting ticks and crosses on the values that do and don't apply. And then you need to put boxes around the probabilities that you want. So if you want probabilities at this end, okay, you can box those off, but you might have to look up a probability at this end, okay? So you need to decide how to draw the appropriate box, and then you use your calculator, okay? And your calculator, you're going to be using binomial, and you can get away with always, as long as you do the boxing thing, you can always use binomial CD, and you never actually have to use binomial PD. So from the binomial CD thing, it'll just be one boxed probability that you'll need to look up and use appropriately to give your answer for part A. Okay, so that's A.E1, I should say. In A.E2, what changes? In A.E2, we're now talking about on more than 10 days but fewer than 20 days, and now it's during an 8-week period. Okay, so 8 weeks, 2 weeks is 10 days, so 8 weeks we're going to have in part A2, we're going to have the same value of p, but we've got a different value of n. So we'll have n equals p equals, okay, and now we want the probability of this particular range here, okay, so you're going to need to do the outcomes, 0, dot, 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 we're interested in values around 10, dot, 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 we're interested in values around 20, and then it goes all the way up to the maximum, whatever n is, and you need to draw appropriate boxes around this to isolate the probability on more than 10 but fewer than 20 days. Be really careful with words like more and fewer. Think hard about whether it's allowed to actually be 10 days or actually be 20 days. Well, for this one here, more than 10 days, no, it can't be 10 days, so you're going to have a cross on your 10. Okay, so put ticks and crosses on, get boxes. In this particular case, there are going to be two boxes, and you're going to be subtracting two values from binomial CD. Okay, so that was part A. And part B, we've got, again, we're assuming that Trina's claims are still true. We're going to get the mean and standard deviation for the number of times during a week. So this is now a new value of n again, that the train arrives on time for the station. So in B.E1, B1, okay, we've got n equals, we've got p equals, we've got the mean, okay, which you can call expectation of x, or you can call it mu, equals, and you're going to use the formula from your formula book, okay, for the binomial. You don't have to memorize these, but you do need to know where you find them. And similarly, what's the other thing we needed? Be really careful reading it. We want the standard deviation. So the variance is what you've got a formula for. So you quote the variance formula and get a value for that, but then remember that the standard deviation is not the variance. You have to adjust it. So the standard deviation equals, okay, and that's your value of sigma. Okay, so then what do we have to do? All right, we have to look at some data that's given. So we are following Susie, who's recording the number of times the train arrives on time at the station, and these are Susie's results, and we've got to do a mean and a standard deviation of these values. Okay, so we've got a list of data, and we have a calculator, so we're going to go into our ordinary statistics mode, and it's just a list of data, so we're going to be using 1var, and out of this we're going to be getting an x bar and an sx value. So in your solution, okay, you just need to say from your calculator x bar equals and sx equals, and then you've got to comment on the likely validity of Trina's claims. Now they've pretty much set up clearly what they want you to do. You've got some calculator values, so the mean and standard deviation of the sample. You've got the mean and standard deviation for the binomial distribution, and you've got to make a judgment about whether they're a good match or not. And don't worry too much. If it's sort of in a grey area, then sometimes they give credit for clearly stating which you think. So make your own judgment. Is the match good enough? But then make sure you draw a conclusion about Trina's claims. Okay, she's made a couple. She made a claim about the probability and independence. If they're wrong, we probably won't be able to tell which is wrong, but we will be able to say whether we think from the calculations we've done, Trina's claims seem to be valid or seem to be invalid.